Hello everyone and welcome to Formula Bharat Driverless Vehicle Workshop 2023. Our topic for today's session is mapping and localization, hosted by Bosch Global Software Technology Private Limited. The topic will be presented by Jadhav Sanket, Senior Engineer at Bosch Global Software Technology Private Limited, and Giri Gunjan, who is an Associate Software Engineer. All participants are requested to note the following general instructions. We encourage you to turn on your video during the session. Please mute your microphone throughout the session unless you are asked otherwise and during doubt solving session. So without further ado, let's begin the session. Over to you guys.
Yeah, sure. Uh, am I visible and audible clear?
Yeah, you are.
Yeah, give me a couple of like a short 2 minutes. My colleague is trying to join. Give him just 2 minutes. By the time we'll share the screen and you guys can have a idea of what we'll have a good discussion of what exactly odometry and stuff are. Uh, just a second. Is my screen visible to you guys?
Yes.
Yeah. So as you guys all know, today's topic is basically on odometry. So on today we'll discuss much on the side of what is visual odometry, what is lidar odometry, and different kind of odometry that we can basically derive from multiple sensors. And having started with that, just a brief introduction of about myself. So hello guys, this is Gunjan Giri. I'm born and brought up from Rourkela, Odisha, and I'm presently associate software engineer associated with Bosch for like from the past 1 year. And we work in a experimentation platform known as ACE, where we develop algorithms and test so as to validate our algorithms and check how much our algorithms is good enough to be tested and deployed on the real life autonomous vehicles. Having said that, my hobbies said as in like I'm a avid robotist. By the time if you guys check me on LinkedIn, I will be definitely sharing some of the codes or some of the circuits or any of the things that you can see up. So yeah, that's pretty much from my side as a person who I am. And let's move ahead with my colleague Sanket. I hope Sanket is Sanket's video and stuff are fine enough. Yeah, let's move ahead with Sanket.
Yeah, hi guys. My name is Sanket Jadhav. I am born and brought up in Pune. Currently, I am working as a software development engineer in the Bosch in the field of autonomous driving. I have 1+ years of experience in the field of SLAM, which stands for simultaneous localization and mapping. I have completed my BTech from Triple IT Pune in the field computer science and engineering. My hobbies include sports. I follow cricket and football, and in my free time, I love solving DSA problems. So yeah, basically, I do competitive programming. That's all. That's the short introduction from my side.
Ye- Yeah, guys. So I hope it's pretty much known about what we both are and what we do in Bosch. So yeah, let's move ahead with the present topic that we are going to discuss for today's session. So before starting with the odometer, like I hope like you guys can interact with us. That's completely fine. And so before starting with the topic, I just wanted to know if you guys have like, do you guys know what is odometry or anything about odometry when you hear? Because you guys must have paid for the session, correct? So you kind of should have like researched about it. So yeah, anything that you guys think of what odometry is will be really good to hear from you. Then we can start off. Anyone?
Briefly, we can say that odometry is glance of all the parameters as we speed, distance, and all that stuff, I guess.
Okay, partially correct. Anyone else? Like a good answer. Anyone else want to speak up? Okay, so let's get to a bigger topic. So before entering into odometer, let's first see on the broader picture what is localization, because from localization we derive the odometry issue. So yeah, so what do you guys understand by the term localization? Let's start from the base. Anyone?
Localization in terms of lidar and optics can be recognition and like identifying all the objects around us and then mapping
Uh,
them correctly at which distance they are located.
uh,
It's
okay.
just my guess. I'm just new
Yeah,
to.
yeah, 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 definitely. Definitely fine. We just want the session to be interactive, so that's
Yeah,
completely
yeah.
fine. Everybody can put up a guess, and that's pretty good. So yeah, so to solve on a bigger topic, so what localization means is basically, let's say you are, do you guys know a spotlight in the middle of the sea? Correct. So the spotlight, what exactly does is it gives you a specific location or a specific target with respect to which you are in the sea. Correct. So when we say the localization, so it's basically kind of you know your position with respect to the surrounding where you are. You might for a new for a better understanding of you guys, I like you can say you are having a GPS sensor. So what GPS sensor gives you is the exact coordinate of where you are with respect to the world coordinate, like with respect to the map. So that is what localization is on a broader picture, if you guys want to know. And when we say localization, it's like kind of unsolved problem in the autonomous world, because there you never know when the environment can change around you. So getting localized with respect to the unknown environment is still a ongoing research that is going on for the timing. And having said that, on the localization side, my colleague will say what exactly is odometry and stuff. So yeah, over to Sanket.
Yeah, localization is in a broad way, it's a absolute term. So we are given the map and we have the absolute position where we are standing in the map. Odometry is kind of a local estimation. Um yeah, so odometry is the local estimation of your poses. Um on an interval of a time, odometry can drift. So we cannot trust on the odometry completely over a period of a time. But odometry usually is a good estimation that we can feed in our SLAM system. Yeah, so that's the basic and the subtle difference between the odometry and the localization. So odometry is a relative term. So and localization is an absolute term.
So
Yeah.
so yeah, I hope you guys like now have a good understanding of what localization odometry is. Moving on with the other terms that we are supposedly going to use in the whole session. So as said, odometry is the estimation of the relative ego motion. It's like it's a relative term. We really don't know where it is. And having said, there are multiple other terms that we use. One is slam, one is transforms, one is navigation, one is plan. Like these are the other technical definitions or terminologies that are normally used in the autonomous systems. So having said that, will like me and my colleague will give you short description of what individual topics are. So having said that, starting with transformation. So while we go on to the whole session, one of the biggest term that you will hear in the whole session will be transformation. So what does exactly transformation mean is like when you move from one point to next point, you get you basically get a coordinate. So in robotics, the coordinate is in the format of transformation, like x, y, z, and some kind of rotate. So translation and rotational coordinates. So let's say you are in the PPT as well. You see in the visual odometer, when a car is moving from one to next, there is a small R and T value. So that R and T value is basically known as transformation, like with a transformation matrix, which indicates how much my car has moved from one place to another place in terms of rotation. Like rotation may be some kind of matrix, and translation some kind of matrix, because our robotic systems understand matrix forms. So yeah, that is basically what do you mean by transformation. Next we'll move with the term mapping that my colleague Sanket will say.
So yeah, in the mapping, we usually try to build the map of the environment. Now, map can be of different types. So when we prepare the map from the lidar, so it is an unstructured map. We usually get the lidar point clouds, and yeah, with the map, we say that where is the vehicle with respect to the map. Map also, there are different types of map in the industry that we use, like HD maps, vector maps, and so on. Um, yeah, map is just building the structure of the environment that our robot can perceive and make decision based on the landmarks that are present in the map. Yeah.
Yeah, so these are certain terminologies, like rest of the terminologies that I said, navigation and path planning, that I want you guys to deep dive into and search, because that are not the scope of this session. But yeah, I hope when you dig deep into it, you will definitely find a good explanation, and will be definitely useful for you to research upon that. Having said that, let's move on to the next topic. The product, like the whole the system of what we are going to have today. So when we said odometry, like there are multiple types from where we can drive odometry. So basically, for our use case and autonomous systems, we rely on sensors to get the odometry values, and that is how these three odometry types are defined here. One is ladder odometry, one is visual odometry, and one is fusion based odometry. And there could be multiple other odometry packages and odometry stuff that we can do, but predominantly these three are the basics and the base of where we can start ahead with what exactly odometry are. And on today's session as well, will give you a brief understanding of all the three kinds of odometry, and will get you through the whole intuition of why do we use, and a small code snippet that we guys, like, that you guys can take up as a task to, like, implement the whole thing on a ROS, and you guys can show it up to us, and we will evaluate it for you guys. So yeah, having said that, let's move with the first topic for today's session, that is ladder odometry. So yeah, before starting with the term ladder odometry, like, I hope you guys are clear with all the terminologies and all the things that I have been saying from the past couple of 10 minutes. But having said that, uh when you guys hear the term lidar odometry, what do you guys understand? Like, what does the naive thing that comes up to your mind when you hear the term lidar odometry? Anything, anyone can, like, it's an open platform. You guys can definitely discuss and say what do you guys understand, what do you guys mean by the term lidar odometry. Okay, I feel the participants are sleeping, I guess, in the session. But but yeah, that's okay. So when we say ladder odometry, the whole odometry, when we hear the term ladder odometry, it's like kind of deriving the values from the lidar sensor as a time being. So basically, the odometry that is derived from, or that is got from lidar sensor, is known as the lidar odometry. So so then comes, like, what exactly is lidar sensor? Like, there are a lot of stuffs and a lot of things that we said around ladder odometry, ladder sensor. So there must be a question in your mind like what exactly is ladder sensor and what exactly it is. So before going into what ladder sensor is, let's talk about its working principle. So the ladder sensor basically it emits pulsed light waves from a laser into the environment, like kinds of sense scans and waves for like kind of a laser scan to the environment, and then these pulses bounce off the surrounding objects and return back to the sensor. And then the sensor takes the time at like it calculates the time at which the scans go and return back to the sensor, and that is how we determine the distance and like the coordinate, basically xyz coordinate of any of the obstacle or any of the of any of the things in the environment. So this is how the sensor works, and this is the underlying working principle behind what ladder sensor is. And on the right side of the slide, you guys can see a sensor that I have shown you. That's basically a VLP. That's a velodyne sensor. So there are multiple other sensors on the market, but the predominantly the sensor that is dominating in the sensor in the lidar industry is velodyne, and this is basically a VLP 16 channel lidar. You guys, there are multiple other channels lidar known as VLP 32, VLP 64, and when we say VLP 32, VLP 64, 32 is basically the number of channels, 64 is the number of channels, and rest other things. So 16 channel as in it will emit 16 scans to the environment. When we say 32 channels, it emits 32 scans to the environment, and when we say 64 channel, it emits 64 scans to the environment, and it gets back the data out of it. So yeah, so this is pretty much the working principle and the underlying theory of what lidar sensors are and what is its working principle. Having said that, we'll move to what exactly scans are and stuff. But before that, do you guys have any questions here? Like we are open to discussion. So if you guys have any questions till now, you can definitely ask up.
Hi
Anything from
Gunjan,
your side?
Kunal here.
Yeah, say.
Yeah, so you were telling about 16, 32, and 64 channels.
Yeah.
So, according to me, like, is it the frequency or like how does the 64 channel helps as compared to the 16 channel? Is it the accuracy or the mapping or
Okay.
the like frequency?
Yeah, so when we say 16 channel, 32 and 64, so basically, okay, so in the next slide, I would show you here you can see the scan images, correct? Like on the
Right.
right side, you can see scan images. So there comes the difference between the 16, 32 and 64 channels, LiDAR's point of view. So on 16 channel, when, okay, let's say you have a tree. Let's assume you have a tree, and when you send 16 rays of light on it, and when the rays
Right.
come back, so the data that you get from the 16 channel will be very less, correct? Like it will
Right.
be accurate but very less. But when you on a tree, when you send 32 channel data and when you get back 32 channels reflection, so that data will be more accurate, correct? And like
Okay.
more dense and more accurate. So that is how the channels differ. Like people, depending on the use case, people go for 16 channel, 64 channel, 32 channel, and multiple. And upon the increase of the channel, the costs of ladder, as ladder is a very costly sensor, so upon the increase of the channels, the cost of ladder goes on increasing.
So
So that is,
basically, we
yeah.
can say it's the detail of the object.
Yeah, perfect, yeah, exactly. So you can say the detailing of the object will be more good depending on the more number of channels.
Okay. Okay. Thank you.
Yeah. Anybody else is having any questions? Okay, guys. So let's move with the next part. So having understood what LiDAR sensor is and what LiDAR sensor do, so let's deep dive into what LiDAR odometry is exactly. So before, as I said, like the LiDAR odometer, like the LiDAR sensor releases scans, correct? So on the right side, you can see this image. So this is how the LiDAR sensor releases scans, and you can see the circular rings that is coming out, and the like semi-red and kind of deep red color. Those are exactly the scan images a LiDAR sensor like lidar sensor releases from it, and depending on the bounce back from the environment is what it takes back as a point cloud data or scan image. So what exactly a lidar based odometry is, it's like it takes a point cloud and computes the motion of the lidar between two consecutive sweep. Basically, uh, when a ladder moves from one point to another point, let's say it was at x position, and when it moved to del x position, like x plus delta t, so the distance between the x and del x delta t is delta t, and that but like the motion between this delta t will help in getting the odometry value of the object or of the car in the environment. I know this is something like would definitely go out of your brain for the time being, but by the end of this ladder odometry session, I am pretty sure you guys will be able to understand what exactly ladder odometry is. So yeah, so just to have a brief overview of what exactly ladder odometry does. So on this left side of the PPT, you can see the black line. So the black line is kind of the ground truth. So when we say the ground truth, it is like the that the trajectory that the autonomous systems of the car have moved around the environment, and the red line is kind of the lidar odometry value that is generated from the lidar sensor for using the autonomous vehicle. So that much accurate is lidar odometry, what we can see from the image. Correct. Let's move with the next slide. So before starting with what exactly ladder odometry is, let's have a brief overview or the brief architecture of what exactly is it is, and the understanding of it. So when we say ladder odometry, it basically works on the four underlying principles. One is fetching ladder scan, getting the data pre-processed, then do scan matching, and then we update the odometry values. So this is how basically the architecture of ladder odometer is all about. And when we say this all four topics, well, deep dive into every building block of what exactly the fetching ladder scan, pre-processing, scan matching, and update odometry are. So let's start with the first topic, which is like fetching ladder scans. So yeah, so when you guys hear a term fetching ladder scan, it's as simple as you guys can think: getting the raw point cloud data using the ladder walking principle that I made you guys understand. Like it sends back data, receives the data, and then after receiving the data from the ladder point cloud, it like visualizes the scan. Like we get n number of point clouds, so we then visualize the scan of how does the ladder scan looks like on a raw, like every sensor what that we get in today's world is kind of noisy. Like nobody can guarantee that a sensor gives out perfect correct data out of it. So every sensor that we see or that we get on the real market is kind of noisy a bit. So the first thing that we do is like we receive the raw point cloud data using our ladder working principle, and post getting the data, we visualize the scans just to see how much is it noisy. So when we say we visualize scan, we visualize scan with comparison to the image, like the camera image, just to see how much my scan is accurate with the time being. And post that, after visualizing scan, we send the data to the pre-processing method, as this is the second building block or second block of the architecture of the ladder odometry. I hope till here the concepts are clear for the fetching ladder scan. Correct. So next, moving with the pre-processing. So when you guys hear the term pre-processing, so what exactly pre-processing is, like kind of when you receive a data, then you do something or the other on the data to make it accurate and to make it useful with our use case. So on ladder odometry terms, what exactly pre-processing is like, on here we first downscale the data based on our cluster size. So now you guys must be thinking, why do we downscale the data? So this particular downscaling of the data will be, you guys will be clear about it, why do we do, and it will be you guys will be automatically understanding like what exactly the what why exactly we do downsampling or downscaling. And then we fix a region of interest in which we require data. So as I said, the lidar scans that it releases, it's like 16. So if it's a like Basically the lidar sensors that we get, those are dependent on the degree of like how much it moves. So there are 120 degree of freedom or 360 degree of freedom, and depending on that we need to fix a reason of interest on which we require data, because we really don't require the data of the whole environment when we do lidar odometer, because we only need the values that are in front of us, not at the back of us, or like depending on the situation. There could be scenarios when we definitely require the data that is back of us, but considering the situation and considering the scenarios, we fix our region of interest, like gathering the data that is required for our use case, and then making the points in the ground plane. So this ground plane and surface normal is one of the concept that is a parallel concept of scan matching, where we do point to plane. That will make you understand in the next slide. So I hope you guys are clear. Tell why do we do pre-processing and why do we require pre-processing, like why is it required and why do we do a reason of interest thing here in the pre-processing steps. Any
Yes.
questions from you guys? Yeah.
Yeah, Kunal here once again. So,
Yeah.
like downscaling of data is like their LiDAR cloud points, right? So,
Yeah.
how do you downscale that? How do you
Okay.
detect
Yeah.
that these points are the noise and these points are the important points?
Exactly, that's what. Okay, I didn't make you understand well. I was planning to do that on the scan matching, but okay, let's if you have said the term, so let's start with that. So when we say downscaling of data, so if it is possible, okay, by the end of this session I will show you how the point cloud data looks like, and post that you will see why exactly we require downscaling. So on a layman term, when I say when we get that point cloud data, the point cloud data comes as a million of points. So it will be millions and billions of points that we get from a particular object. Correct.
Right,
And when we receive thousands and millions of point, we can't really take every point, because okay, in scan matching what we do is like we see from a particular scan and we then see for the next scan where it is. So let's say you can't really match millions and billions of point with the next scans millions and billions of point, because that
right,
is not computationally possible. Correct. So
right.
that is
Yeah,
how you downsample the point, and that is basically depending on the cluster size. So this cluster size is basically what we think as kind of like a value that we see. Let's say my if around a radius of 0.35 there are cluster of point cloud data it is, so I will consider it as a good point and I will send it for my scan matching. So that is how
okay,
we downsample the good points from the noisy points, and those good points are the one that we send for the scan matching algorithm to pre-process and to make data out of it.
okay. So, like we
Correct.
fix the number of like this is the baseline of the
Exactly.
LiDAR cloud points, and if there are cluster of points above this baseline, then it will be considered important and considered for
Yeah.
the scan. Okay,
Exactly. So basically, downsampling is kind of getting good points so that we can, because we can't really send every point that we get to scan matching. So we
right.
need to fix certain number of points, and that is why pre-processing and whole stuffs are working here.
Okay, okay, okay. Thanks.
Yeah. Anybody else? Any questions? Any doubts till now? Okay, cool. So let's move with the next building block of the ladder odometer, that is scan matching. So what exactly scan matching does, it's like it finds the transformation that aligns two consecutive point clouds, and it's basically the work is to minimize the difference between 2 point clouds and give back transformation. So as simple as these terms would mean, it is not as simple as that. So when we say scan matching, it we narrow down the scan matching into three types down here. One is point to plane, point to point to plane, and symmetric based scan matching. So when you hear a term known as point to point or point to plane or symmetric, what is the thing that is coming to your mind? Like in the previous slide, I made you understand what exactly point to point and like some part of the scan matching. So after hearing, what do you guys think could be point to point or point to plane, or what do you think is scan matching exactly? I just want to have a brief or a naive idea from you guys.
According to me, uh, the lasers are in 360 degree, right? Like in XYZ
Yeah.
direction. So point to point is considering the origin of light, like laser from the sensor to the surface and back. So where the if we consider a plane, then the point on the plane is I guess so, point to plane, and point to point is on the surface, I guess. I don't know much about these terms. It's my guess.
Definitely. Yeah, definitely. We just want to hear the guests from you guys only. That will make
Yeah,
the session more interesting. It's not like
yeah,
I
yeah,
will
yeah,
be only speaking. So yeah.
yeah, yeah.
Any more, anyone, any more people wants to say? Okay. Okay. So having said that, so what exactly point to point or point to plane means is like as I have wrote in the slide, finding the spatial transformation that aligns two consecutive point clouds. So what exactly two consecutive point cloud mean is like at, let's say, at a position x, like xy coordinate in the world frame, your lidar releases a scan, and then my vehicle moves, let's say, some delta x. So at my x plus delta x, it releases another scan, and then at x it releases a scan, and in every scan there are a series of point cloud data, and in x plus delta x there is another scan that has a series of point cloud data. So what exactly the things happen is it kinds of tries to see those number of points in x and x plus delta x values to see where exactly, like it tries to match the number of points or the number of clustered points, where does it exactly lie, like it kind of groups the values in x, and it tries to see where does those clustered points see in my x plus delta x. And whenever it sees those actual number of points in my x plus delta x, it kinds of finds a relation and kinds of find, yeah, these are the sets of points that are matching to my previous scan. And then from that it uses a mathematical equation there, and it gets the transformation values out of it. So this exactly is what the baseline algorithm of the scan matching. And the algorithm, the thing that I made you explain is exactly what point to point is. So what point to point does is, and in the previous scan, like in x, the in the number of in the x, the scan that has a point cloud data, it kind of forms a clustered points, and in x plus delta x it kind of forms a next set of clustered points, and it kinds of tries to match both the points from this point, like in x the points, and in x plus delta x the points, and it kinds of tries to create the match between two sets of points, and from the two sets of point it kind of determines the transformation. So this is exactly what point to point is. And then comes to the next term, what is point to plane. So when you guys hear the term point to plane, so what exactly point to plane does is like, as I mentioned, the odometry or the scan matching happens between two consecutive scans or two consecutive point clouds. So here again we take the term as x plus delta x. So in x it has a number of from the scans it has a number of point clouds, and in delta x it tries to create a surface normal. So basically it has a set of point cloud, it tries to get the normal to the ground plane, and it creates a baseline out of it. And then all the points, all the clustered points that are in the x points, it tries to project it on the x plus delta x plane, and wherever it tries to match the plane or match the line, it kinds of says it is a good match, or it is my scan, the scan matching algorithm has got the good number of points, and it gives back the transformation out of it. So the whole algorithm or whole the baseline of scan matching is basically tries to match two sets of point cloud data from two consecutive scans and gives back transformation. And there is another term that it gives, that is in layer RMSA, but that doesn't really require in our use case. So we particularly will take up the term as transformation. So between two point cloud, it determines the it determines the scans and determines the point cloud, and it gives back the transformation out of it. So yeah, so I hope the scan matching thing is right now clear with everyone, like what exactly the baseline of scan matching is and what exactly scan matching does. Any questions here? Hey Sanket, am I audible?
Yeah, Gunjan, you're
Okay.
Uh, from my side, it's getting a little bit distorted. Is it the same for all
Uh,
of this?
okay. Can you guys say me up like is it same for everyone?
Hello, Dikshita ma'am. Can you just confirm? Is it getting distorted from your side? Or I guess Sanket can also tell us.
maybe Kunal, you can rejoin the session and see if the problem is getting solved or not.
Sorry, can you repeat? It was distorted from for me.
I think the problem is from your side only. Maybe try to
Yeah, yeah,
rejoin.
yeah. Sure, sure.
Yeah, okay, so I think the scan matching algorithm is clear to everyone. So now let's move to the final part of what the final building block of the ladder odometry is. So here what we do, as we got the transformation values from the scan matching. So right now what we do is we multiply the transformation with the previous odometry value to get the updated odometry. So what exactly it happens is we all like for the baseline of the algorithm, we definitely need a starting part of the odometry value. May it if we don't have, we consider it as a center 000 or anything. So and from that we try to get the transformation from the next scan. So what in hybrid odometry step happens is like kinds of finds the transformation between two consecutive point cloud data, and then it gets the transformation out of it, and it then multiplies with the odometry value on the previous to get to the next odometry updated value. And this process continues on an iterative side, and this till my process till my autonomous system doesn't gets a good next updated value of the odometry. And so for this only, the algorithm is known as iterative closest point, and this is one of the scan matching algorithm that we have covered till here. So what exactly is it is it's like the whole algorithm that I told you, from starting from getting the scans to pre-processing to scan matching to update odometry. This whole things goes on in a loop for endless number of time till we get the number of scans. And till the time we get the number of scans, we kind of create and update our odometry, and we get the final value of the odometry is up. So yeah, so this is one of the method of finding the odometry. The other method is basically NDT, which is normal distribution transform, and that basically will one of my colleague will have a session tomorrow. So he will make you understand what exactly NDT is and what exactly NDT does. So on today's session, you understood what exactly one kind of scan matching algorithm it is. I hope you guys are right now clear and clear with the basics and intuition of why we do the ICP based thing. I have a question definitely for you guys, but yeah, I want to hear if you guys are clear with the concepts or not.
Yeah, it's clear for me.
Yeah, fine. So the question that I wanted to ask is, so I made you guys understand there are two kinds of scan matching ICP algorithm, right? One is point to point and one is point to plane. Correct. So what do you guys think is beneficial or is mostly used in the autonomous systems world? Like what do you like which algorithm mostly people use to get the odometry value in the autonomous systems according to you people?
Hi Gunjan, Kunal here. So,
Yeah.
if we talk in simple terms, we want to just lower the processing for the processor, and so if we want to reduce the processing data processing process, I think point to plane is beneficial for the processor. If we like, if the I guess Point to plane will reduce the stress on the processor to process the whole process.
Okay, okay, good. Anybody else? Any and like any other people wants to say something? Okay, so may I know your name?
Are you talking about me, Kunal?
Yeah. Okay, yeah. So yeah, exactly. What Kunal said is exactly correct. So we normally use point to plane because the point to plane is computationally less heavy than point to point, because in point to point every scan points we take into account and match with the previous scan, but in point to plane we kind of match with a plane surface, so that it whenever it finds a good match, it takes up the data and it processes and gives out back the transformation. So yeah, the point to plane is one of the way and is mostly used in the scan matching algorithm in today's world. Having said that, there are different ways of scan matching. As I said, like one is ICP, one is NDT, and on this ICP and NDT, there are multiple inside like use cases as scan to scan, scan to map, map to map, and feature based. So basically, the scan to scan, scan to map, map to map, and feature based are the terminologies that are basically used in mapping side. The scan to map is basically your lidar releases a scan and it tries to match with the lidar point cloud map data, so that it determines where am I localized, or where am I standing with respect to the map. And in map to map is kind of you have a map around and you try to get correspondence with a bigger map, so that is where the map to map kind of scan matching things happen. So these are certain ways of how scan matching happens. Now let's move to a Python implementation. I hope like we are running a lot with the time, so I won't really go deep into the Python notebook implementation. But before that, I will let's see this GIF. So just a second, let's show me the code. So I hope you guys can see the code here. So this is basically a open source code that I took from Venki Desai. He has kind of he has written a ICP code, and this is basically what this code does is it takes like this x pcl x.txt has a previous odometry value, and the pcl y.txt has the next odometry value. And as I explained you guys, so basically what this thing happens is the whole algorithm works on finding the perfect like downsampling and getting the good points out of it. So this function basically here estimate correspondence, takes up the values, finds good correspondence points, and stores it in xc and yc values. And then this xc and yc values determine the transformation, and depending on the previous scan, like this function kinds of get you the good points, and then this function kinds of find the transformation values out of it, and it gives back q, and here it kind of multiplies with the previous value and gets you the new odometry. So this basic code will make you this code will be shared to you guys, so that you guys can take it as a reference and can definitely use it for your use case. But for sharing of the this well just a second. Yeah, I hope my ppt is visible. You guys can see the yellow thing that is moving from blue so the blue is the previous odometry, the red is my new odometry, and the yellow value that is moving from blue to red is kind of determining, and it's kind of getting the transformation at every timestamp and kind of multiplying with the previous odometry to move to red odometry, to move to the new odometry, that is why. So this is the whole basic algorithm, and this is a whole baseline of how the ladder odometry is. And the notebook that I showed to you, it will be shared to you so that you guys can have it up and can use it for your respective use cases and your project works. I hope with this the ladder odometry concept is pretty clear to you guys, and it's pretty much it's pretty much evident, and it's pretty much understandable by you guys. If you guys have any question, then it's definitely welcome to me. So yeah, if you have any questions, then please shoot up. Then more after that, my colleague will start with the visual odometry. So yeah, anything up from your side?
Can you just explain in more detail about blue to red? Like, if you're saying that from blue timestamp to red timestamp, how
Okay,
much difference is there between these two timestamps, and at what
okay,
frequency are we
okay.
noticing the
So
difference?
here when I say the timestamp and it's basically okay, the terms that I used here was on the robotic side, but basically in here what is happening is the blue one that you see here, the blue color points, those are the when I showed you the PCLX dot data, correct? PCLX dot txt, these are
Right.
the old odometry values, and then these red are the new odometry values, correct? Like these
Right.
for sure, when we never really have the new odometry or new point, like new odometry values out of it. So what exactly here it is happening is it kinds of from this blue value, as I said it okay, so the in the whole pipeline, the fetching of data has been done. The fetching of data has been done in the pclx.txt and pcly.txt file. That part
Okay.
is done, and then we do the like we do the pre-processing, like downscaling and getting the good points, correct? And this
Right.
is what, and this is what is done in this function. So it's basically find the correspondence points, which is basically getting good points out of it. I explained you there in the point of point clouds, and here it is kind of the array format where we store all the values that are the good points to me. And after getting the good points till here, we get some pre-processing thing is done. After pre-processing, I explained you there will be the scan matching algorithm, correct? So what that,
Okay.
and from the scan matching algorithm, what happens is we get the transformation values, like the rotation and the translation matrix, correct? And this
Okay.
function what exactly it does is it finds out the translation and the rotational matrix out of it, depending on the previous scan, and some mathematical equations out here. And post that, when we get this values of the transformation and my good scans, I multiply here with my previous values like pclx dot data with my rotation and translation value to get my new data, and this is my new odometry value, correct? And this
Okay.
new odometry value is what you see here. It is moving in, like the yellow thing is what exactly the new odometry value that you see moving.
Okay. 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 So like how this data is useful in the SLAM? Like, why
Okay,
does the company wants that data?
uh as in I didn't get you, like can you come again?
Like, is it useful, or is it like just a lesson, or uh, some topic which we are discussing, or is it really useful in the
um
industry?
okay, not really, not definitely not really, it is definitely used in the industry. So what I showed you here is the very naive term, or a very basic term I would say on the odometry side, like having two values.
Okay.
And but on the real autonomous systems, when you see a car around, you will see, but okay, by the end of the session I will show you a real life autonomous vehicle, how does it look. So every autonomous vehicle has a lidar sensor, and this lidar sensor releases the scans, and that the first at the first timestamp the scan is the blue value. Like let's say on the real autonomous vehicle side, you see this blue value is the first scan, and this red value is the next scan, like let's say x plus delta x scan, as I explained. So then kind of it
Right.
finds the transformation, and then it finds the next odometry. So depending on the two scans, every two consecutive scans, it finds out the transformation and puts up. So that is how I determine where am I located in the map. And this similar,
Right.
let's say if you want to have it in the slam side, as you said you want to know it on the mapping side. So in mapping, let's say this red, consider this red as my map environment. Like in my map, this is my point cloud data, and this blue is a scan from my vehicle lidar point cloud vehicle. So right now what happens is this blue will try to align with my map's red value and see where it is, and then it kinds of find the transformation value, and then it multiplies with the blue value to get the accurate or the concurrent value of my xyz, and that will be my localization parameters or localization value of where I am with respect to the world coordinate. So the thing that I made you explain is like the basic building block. On top of it, you can definitely use it in slam, you can use it in localization, you can use it in various other concepts that is used in the present industry.
Okay. Okay. Got it. Got it. Thanks.
Yeah, I hope all of you guys doubts are clear. So, and I guess I have taken a lot of time. So let's move with the next part of the topic for the presentation. It is visual odometry. My colleague Sanket will start with the visual odometry. Are you ready, Sanket?
Let me share my screen.
Sure.
Okay. Yeah. Uh, yes, my screen is visible, right? Am I audible? Hello? Okay.
Yes, yes, you are, and your screen is also visible. Thank you.
Yeah, yeah. So Gunjan has explained about the LiDAR odometry, but one natural question that should be coming to our mind is why go for visual odometry? So yeah, any guesses like why are we solving the same problem but with different sensor?
Yeah, I
Here
guess
in visual
it's
odometry we
for
are
the.
using camera. Yeah.
Yeah, I was just saying that I guess it's for the object identification. So lidars are basically good at detecting the distance, but they are not good at identifying the objects. So that's why I
But
guess we are.
do we really need to identify the objects as in to
Yeah, of
estimate the
course.
odometry?
Is it are the objects moving or are they permanently fixed in the environment? So like buildings and trees are permanently fixed, but if they are bicycles and persons, then they are movable. So they will be classified as different objects.
And how are we going to use the moving objects? Like why are we
For that,
definitely, I mean, focusing on the moving obstacles? Yeah, moving objects.
because they are not predictable and they can be like in the autonomous driving systems, safety is much given much more importance. So we treat them much in like they're the main point of focus. So that's why.
Yeah, you are kind of correct. See, one thing is like if we have our LiDAR points on an moving obstacle, our scan matching will definitely become more difficult. So we can definitely remove the scans that are on the moving object, right? Does that make sense to you?
Right.
Correct, no?
Can you just come again?
Uh, to want our scan matching. So till now we have some idea about the scan matching, correct? So in the scan matching,
Yeah.
we were having the LiDAR points.
Right.
LiDAR point in the frame K and the LiDAR point cloud in the frame T plus 1, next time step. And
Right.
if the LiDAR point clouds are not stable, I mean, then it will deteriorate our scan matching results, correct? No.
Right. 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 True.
Our map environment should be static. If it's totally static, then we are bound to get the good scan matching results. But ideally, this is
Right.
not the case.
Right.
So how will LiDAR figure out that LiDAR sensor? That is really tough
Right.
job. But through
Right. Right.
camera perception, we can figure out like if the obstacle is moving, and we can restrict our algorithm to select only the feature points that are on static obstacles. Correct.
Right. Right. Right.
Yeah. But the basic thing you are missing out, like why go for camera based odometry? Can you just Google out the price of LiDAR?
Yeah, I know about that also. Yeah, there's a very good price difference between both of them.
A significant there is a significant difference. So people want to solve the odometry estimation problem using just the vision, because cameras are easily available and they are much cheaper than the lidar. So the lidar that we are using in our industry, it cost around 16 lakhs for us. So you see, and the camera that we has is just 30,000.
Oh, right.
So now you get the idea why solve the same problem using the camera based perception, correct? So by visual odometry, what do you understand? Like, it's the same problem, correct? Obtaining the motion of an agent, but this time we are using the camera sensors. And to formulate the problem correctly, let's understand what is given and what are we aiming for. So in the visual odometry, the problem statement is like this. We are given a set of images. So images are coming at every timestamp, and robot is asking us. So we are asking robot to so we just want the poses of the camera at every timestamp using the set of the images. So are you guys clear with the problem? What we are trying to do?
Yeah.
Okay. Here is one small demo that a small demo of visual odometry. Okay, let me just a second. I think there is some problem playing here. Okay, is my screen visible?
Yes.
Okay, so yeah, so this is the small demo that you guys can have a look on. Um, Basically, this is simulated in the Carla environment. This is a fisheye camera model, and you can see the trajectory towards your right side. This is a trajectory of the car that is moving around the town. So you can see how perfectly it's detecting the turns.
So Sanket, is the like trajectory from the camera perception or from the like there's some option on Kala engine to get the trajectory
This
using
is purely from
GPS
camera
signal?
perception. No,
Okay.
this is purely from camera perception. So yeah, let's get back to our presentation.
So is the color coding of the circles in the fisheye for the identification of different objects, or is just there for showing that there are points?
They are just the feature points. They
Okay.
are so yeah, the color encoding here doesn't matter.
Okay.
Okay. So yeah, let's move on. So yeah, pipeline for the visual odometry. First, we'll be having the set of images. Then on that set of images, we'll extract the features. After extracting the features, we'll try to match those feature with the next frame, and we'll send these matched features to the motion estimation algorithm. That depends like what we are trying to do, 2D 2D pose estimation, or 3D 3D, or 3D to 2D. These are basically depending upon what kind of feature points you have. If you have the 2D feature points, then you will go for 2D 2D motion estimation. There are different ways to solve these problems. So 2D 2D pose estimation is solved using epipolar geometry. If we have the 3D set of points, like in LiDAR, we were getting the 3D set of points, XY. For every point, we were having the three dimensions, XYZ. and these were available in both the scans, previous and the next scan. So we can use here ICP. uh, this is a 3D to 2D. We can use the PNP algorithm, where in the first frame we have the 3D coordinates, and in the second frame we have the 2D coordinates. After that, since I have told you earlier that this is the local estimation, uh, on the course of a time the odometry can drift, so we need to do some bundle adjustments. This is out of scope of today's workshop, but yeah, this is usually the pipeline of visual odometry. And this whole thing is sent to the SLAM system. So basically today we are looking at the front end of the SLAM system. I think it's clear what are we going to study today. Yes.
Can you just tell me the example for 2D to 2D? Like in which case 2D to 2D is used?
Okay, so let's consider the image. In image, if you extract any point, so in image, if you try to extract any point, that will be a pixel, correct? A pixel we denote by u comma v. If we want to know
Okay,
the
in
location of
that
any pixel,
okay, in that sense.
uh,
Yeah, yeah, yeah. Okay,
yeah,
okay.
got okay. So yeah, from the lidar sensor, we were directly getting the points, okay, feature points. But how do we obtain from the camera sensor? From the camera sensor, we are getting the image, and it is really necessary to extract the feature points. So how do we do that, and what kind of features do we select? And basic question, what is actually the features? Okay, so we'll study about them. So features are nothing. So in this image you can see these marked points, markers. These are here depicting the features. Features, we can say they are the special places in the image. uh, their properties are somewhat special pixels in the image. Their properties are somewhat different from the rest of the pixels. And the feature point comprises of the key points, basically the position, uh, u comma v, and there is one descriptor associated with each feature point. Descriptor will uh, encode the information about the surrounding of that pixel, and usually descriptor is of 128 size binary descriptor. Today's workshop we are going to study about the orb features, which stands for oriented fast and rotated brief, because of the fair trade-off between the time complexity and feature extraction thing, and the real time we can achieve the real time performance using the orb. This is not the best feature that is available in the literature. We can definitely go for different, there are different kinds of features available in the literature like surf, shift, but we'll study the orb feature today and get a feel like what is the feature point. So I think the feature points you are clear with what we are trying to extract. It is nothing but some special pixel which will have the position, and descriptor which will describe the environment around that pixel. Now let us look how we are going to extract this feature point. Orb features are nothing but they are basically corner features only. So as you can see in this image, this looks like a corner. And now let us study what are the properties of corner, why we are saying it as a corner. If we enlarge or zoom at this point, uh, so let us consider that point as a P. Now this pixel P will have pixel P will have its pixel intensity much different than its surrounding pixel. It may be brighter or it may be darker, but it is definitely much different in its intensity with compared to the surrounding pixels. So that is how uh, we are saying that this pixel point is a feature point. Algorithmically, how we are going to do that? So we'll iterate over each pixel. Uh, Supposingly we have selected this pixel now. On this pixel, we will make one radius of some length r that we can change in our code, and we select a few neighboring pixels and we compare the pixel intensity of the surrounding pixel with our uh, interest of pixel, which is p. So let's say if the pixel's intensity p is greater than some threshold with compared to this pixel, and like that we are finding some 12 pixels on this radius, then we'll say that pixel p is the corner point or it's the special feature. Or other case can be like if the pixel p's intensity is lesser than some threshold than than its surrounding pixels. So basic main idea is that pixel should be different than its neighboring pixel. It should be too bright or too dark. So are we clear with how are we extracting the feature points? How are we knowing about the feature points location? Any doubts in this algo? Yes, guys.
Perfectly understandable. Thank you.
Okay. And yeah, so with the now we have extracted the feature point, but it's also necessary to extract the brief descriptor, which will encode the information about the pixel surrounding. So how are we going to do that? So as I said, brief descriptor is a 128 dimension vector of zeros and ones. And how are we going to assign the values, whether that index will be having 0 or 1? So it depends on, so it is like this: if p is greater than q, then take 1, otherwise take 0. And we randomly ask the algorithm to select some 128 pixel and compare the size of the pixel p with its size of the pixel q, and we randomly fill the 128 vectors like that. Why this brief descriptor is important to compute, we'll get to know in the subsequent slides. So yeah, after we have extracted the feature points, now the step is to match those feature points with the consecutive images. So assume we have the features, m features in the timestamp t, and some n features are extracted in the next frame at time t plus 1. Now our task is to match or find the correspondence between these features in the two images. So one way is to do brute force. Consider each pixel, try to match it with the features of uh, next frame. And in this matching, we are going to use the brief descriptor. So we have the descriptor, let's call it as a D1 for this pixel point, and the descriptor D2 here. What we are going to do is we are going to take the Hamming distance between these two brief descriptors. Hamming distance is nothing but you are taking the XOR of this descriptor, and then you are counting how many bits are on. So lesser the Hamming distance, we can say in the vector space these feature points are closely related, and we associate this feature point with its uh, lesser with whom its distance is coming less. uh, any doubt here?
No, no.
Absolutely correct. Okay. Yeah, next step is after we have found out the matches, we feed these matches to our camera motion estimation algorithm. So here we are going to use PNP algorithm. PNP algorithm requires feature points from the previous frame, current frame feature points, and the matches. Also, there is one more thing, camera intrinsic matrix, that we'll understand what it is in the coming few slides. Steps are like this, like we solve for the initial gaze of rotation and translation. So this is nothing but how much the current frame has moved with respect to the previous frame. So rotation matrix will encode the information what is the rotation of the current frame with respect to the previous frame, and translation vector will encode the information how much it has translated robot has translated in the world. And to solve this, we are using the mathematical tool, direct linear transform. Then we are improving this solution using the Levenberg Markov algorithm. And to handle the outliers, we are using the ransack algorithms. All these things are fortunately already implemented in the OpenCV, so we can directly use them as it is. We'll see in the code also how these things are functioning. Uh, yeah. So let's first now try to understand the geometry of image formation. So assume you are in a room. Uh, you are having some point P. Now point P's coordinates in the world frame is some XW, YW, ZW. There is this camera placed here. Uh, Understand the direction of the axis. So Z axis is pointing in front, X is towards your left, so right, and Y is pointing below, downwards. So since we are perceiving the environment in a camera coordinate system, it is essential for us to convert these coordinates to the world coordinate system, because robot is moving in the world system, world, correct? No. And so there is this relation. We need to find the rotation and translation, like what is the rotation and translation between these two systems. So to convert the camera coordinate, so to convert the world coordinate, we multiply some rotation to this point P, and add the translation. So then we get the point in the camera coordinate system. This R and T in the combined form are written as a projection matrix. This is called the projection matrix, or we can also call it as a extrinsic matrix. Uh, yeah. So now understand. Uh, so this now we are moving to the image coordinate system. We have understood world coordinate to camera coordinate. Now from camera coordinate we are moving to the image coordinate. Same point P is being projected on the image plane. This image plane is at the focal length f, and using our high school geometry, similar triangles property, we can see that x by f. So this is your x, x by f, f is the focal length, is equals to xc by zc, xc by zc. So this is your xc and this is z. In the similar fashion, we have this y by f equals to yc by zc. And in the matrix form, if we want to write, we can write it in this way. So if you multiply these two matrices, you will end up that x equals to f by xc, f into xc by zc. The same equations you will get. Uh, this matrix that you see here is going to become our camera intrinsic matrix. These are the focal lengths, but in the real world, these pixels may not be the square, meaning like uh, in the x direction, it may be elongated. So to deal with that, we have two different focal lengths, fx and fy. Also, like the principal point that we see here is perfectly coinciding with the image plane. But in real scenario, that may not be the case. This point may have shifted to somewhere else. So that information is encoded here with the cx and cy. These are nothing but the principal points. And also image might be skewed. So that skew factor is involved here. Yeah, and to get pixel coordinates from the image, from the camera coordinate, we multiply this camera intrinsic matrix. And you might be thinking like in the image coordinate or the pixel, we have only 2 dimension. So if we want to query, so in the image is just a 2D, but why is there, why is here third dimension? So this third dimension gets lost when we are projecting the point P on the image plane. So new pixel points are u dash by w dash and v equals to v dash by w dash. So these are so basically we are dividing this vector with the last dimension, and we end up with the two coordinates. to pixel coordinates. So that was how we convert from world coordinate to camera coordinate, camera to pixel coordinate. uh, do we have time for we have time? Okay, so let's go into the code now. um, this code is open source. I have taken from GitHub. I'll mention the link. You guys can follow. It's a really good resource to follow for the visual odometry. Here are the basic things that we are just importing the dependencies. We have our dataset handler. So let's look what do we have here in the dataset handler. We are initializing our camera intrinsic matrix. Then we have images, RGB images, and the depth maps. Depth map will have the depth of every pixel. So that means how far is that pixel from the camera coordinate. So that is nothing but your depth. These are the only information that I think will require. Let's see if anything else comes up. Let's see how the first image looks like. Okay, we'll load our data set. So these images are taken from the Carla simulation, and from that we have extracted these images from the Carla.
Sanket, can you just repeat for me the camera coordinate system and global coordinate system?
Yeah,
Like
sure.
I'm still unable to understand the global coordinate system. If it's not a problem for you,
Yeah,
like
sure.
just a brief.
Okay, so we are having just what we can say. So our pixel point, so our features are basically pixel points, right?
Right.
Uh, from pixel point. So here this matrix, this formula denotes the relation between the pixel points and the camera coordinate points.
Okay. Yeah. Yeah. And then we
Correct.
to make it a 2D, we divide it by the W so that it gets converted into the plane formation. Right.
So when we want to query on the image, so we query using the pixel locations u comma v. So these are the
Yeah. Right.
actual locations u comma v. Because in the
Right.
conversion from camera coordinate to image, camera coordinate to image coordinate, images are just the 2D image. We don't have depth there,
Right.
no. It's just 2D image. It's projected on the 2D plane. So
Right.
we lose this depth. This is the depth information we are losing out.
Right. Right.
We just need to keep in our mind this relation, which shows how we convert uh, camera coordinate to pixel coordinate. Vice versa, if someone has given us the camera coordinate points and we want to get the pixel coordinates, so what we can do is we are having the pixel coordinates. If we multiply with the inverse of this camera intrinsic matrix, then we'll end up with coordinate system, camera coordinate points.
Okay.
So basically, if you are
Okay.
having the pixel points, you are multiplying the pixel points with the camera intrinsic inverse of the camera intrinsic matrix,
Okay.
because in the we feature points are in the image coordinates, right? S- So
Right.
we can multiply with the camera inverse of the camera intrinsic matrix and can get the points in the camera coordinate frame.
Okay.
Yeah. So for now, if you understand this is more than sufficient. If you
Okay.
just get the feel of it, like no need to get
Yeah.
in more depth. Yeah.
Okay.
Yeah, I mean our data set is also loaded. So this data set is having the 52 images, sequences of images, and we'll see how our first image looks like. So this is the grayscale image. We usually work in the grayscale image because we are dealing with the intensity, and yeah, that's the point. So its corresponding RGB image is this, and this is the depth map. So red denotes like the point is towards it's the far from the camera. Blue are these are the points that are near to the camera. This depth information we'll be using because we are trying to estimate the motion from PNP algorithm, and PNP requires 3D 2D set of feature points. So this is our camera intrinsic matrix. Mm, 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 mm. Just a second. Yeah. Hmm. So if we are querying at this pixel, okay, depth. What is the depth value of the end pixel? This point basically. So its depth is coming to be something like 1.862, which is like this point is 1.862 meters away from the camera. In a similar fashion, we can check depth of any point just by querying onto the pixel. Mm, So yeah, let's look into the feature extraction. So we are directly going to use the functions that are available in the OpenCV library. We have already understood the underlying principles. How are they extracting the features? So orb create will be just instantiating the object of the orb detector. This detect and compute function will compute the feature points and its descriptor. So basically we are calling uh, on the orb object, we are calling detect and compute function. It will detect feature points, and also simultaneously it will extract the descriptor. So this is key point and the descriptor. It's going to list of key point and descriptors. This function is going to return us. Yeah, let's run this. So now this is saying that number of features detected in frame 0 are 1500. Okay, and the coordinates of the first keyframe. So these are just the coordinates. Key points are nothing but the coordinates of the feature points. Now let's try to visualize the detected feature points. So if you see here, uh, the feature points are marked with the green circle, green dots. And also to notice that we have extracted the orb. You can see that the intensity difference between this point and its surrounding is large. So in one way we can say that we have extracted the corners here. And yeah, you can understand like these are the corners. uh, Now this we since we have done this on the first image, we'll do the feature extraction on set of image sequences. So yeah, second step was to do the feature matching. So let's do the feature matching of zeroth and the first image. Yeah, so in the feature matching, we are calling this function feature match feature, and in that we are passing the descriptor. As I said that we'll be using the descriptors to find the feature matches using the Hamming distance. So we can see the correspondence between this feature. So yeah, these are the matched feature points. Now all these matched features will be sent to the motion estimation algorithm. Uh, yeah, so here we'll estimate the motion. Remember, as I have earlier mentioned, that we are going to use the matches, key points, key points of the first frame and the second frame, and the camera intrinsic matrix. So till now, what we are doing, we are iterating over the matches. We are extracting the pixel point, u1 v1 in the first frame, u2 v2 in the second frame. And since our algorithm needs 3D point in the first frame, so we are going to extract the depth. So depth, so yeah, so we are querying in the depth one array, we are querying at the pixel v1 u1, and we are getting the depth. And now these points, uh, so s is getting multiplied with the this u1, this array, because in our conversion from camera coordinate to image coordinate, we were dividing by the depth. So now we need, before getting the camera coordinate, we need to multiply the depth with the pixel coordinates. So here we are multiplying with the depth. These vectors are getting multiplied with the depth. And since we want the camera coordinate, so we are multiplying inverse of camera intrinsic matrix with this pixel coordinate. And now this point of the first frames are being so they are now converted in the camera coordinate frame. So point in the camera coordinate, so we have point in the camera coordinate for the first frame, and in the second frame we have the point in the image coordinate. Basically, in the first frame we have 3D points, 3D feature points, and in the second frame we have the 2D feature points. Now we are good to go for solving the motion estimation using the PNP ransack algorithm. So this in this algorithm we are passing 3D point, 2D point, and the camera intrinsic matrix, and it will return us the rotation vector and the translation vector. This will encode the information about the rotation between the two frames, and TVC will encode the information about the translation that has occurred between the two subsequent frames. Um, in our case, so yes, this is the estimated translation vector, and this is the estimated rotation. We cannot really make out from this estimated rotation like what rotation has been occurred, but usually it encodes the information of roll, pitch, and yaw. They are nothing but uh, so pitch is like your rotation around the x-axis. So consider this as your camera, and if your camera is moving up and down, so it's rotating around the x-axis, then this motion is termed as pitch. And if it's rolling, so this is roll is around your y-axis, and this is your sorry, roll is around your z-axis, and yaw is around the y-axis. But in our case, this matrix will encode only the yaw information, because we are not changing the pitch, and our camera is fixated on the vehicle, so it's not going to roll. And so basically the all the rotation is happening in the uh, y-axis. So yeah, that's the thing. uh, yeah, now for the two images we have extracted this, we have seen the feature extraction, feature matching, and we have estimated the motion, which is nothing but the rotation matrix and the translation vector. Now let's do it for the, so if we do it for the all set of images that are 52 frames, then we get the 3D trajectory this way. Also, in the, if you remember, I have shown you the demo video. In that we can see the estimated trajectory how it was. This was just a small data set, but it was really, you guys should try out this. It's available open source on GitHub. And yeah, that's all from my, if you have any questions you can ask. Any question?
No questions from my side. I will try the code first, and if I have any, I will let you know.
Yeah,
Thanks for the code.
yep, thank you. Okay, now Gunjan will take up from here. Yep.
Uh, is my screen visible?
No, not
Uh,
yet.
right now.
Yes, it is.
Okay. So just a second. Let me go to the slide. So yeah. So till we get to the slide, you guys right now have heard about both ladder and visual odometry, correct? So again, we are coming up with another approach of getting fusion-based odometry. So why do you guys think is fusion-based odometry is needed in the in like is needed for the time being, or why are we moving towards the fusion-based? Like, what is the root cause of we moving towards the fusion-based approach?
I don't know about the fusion base. So can you tell me about fusion base? Is it based on camera or is it based on? I think so. It's based on camera, right?
Yeah, okay. So the thing that I will be discussing today was not basically on the camera side, but the other sets of sensors that but yeah, in fusion based we can take multiple sensors to fuse and get the data out of it. But yeah, not predominantly on the camera for sure.
Okay.
Uh, yeah. Okay. So we go fusion based because only lidar or from only camera, we the odometer that we get is after we do all the pre-processing and stuff. Still, there are chances of our data getting noisy and we get a false measurement or false readings out of it. So there are high chances that the odometer that we get could be drifted or could be there could be something or the other that we are deriving but not the actual thing that the sensor produces are we taking up as an account and getting the data out of it. And so is why the fusion based approach is used in today's world. Like we get the odometry from multiple sensors and then fuse to get the final odometry value out of it. So that is how the fusion based approach is used. And having said that, there on the screen I have shared you like couple of sensors that are used in the autonomous industry. One is radar, one is camera, ultrasonic, lidar, IMU, and GNSS and HD maps. So from all the sensors you guys can you can derive odometer some way or the other, or you can fuse two or more sensors to get to a final output out here. As we are running very short on time, so I won't be much explaining about what exactly like the whole thing, because this whole session is conducted on some other day. One of our colleague from our team will explain you much better of what exactly it is, but we'll definitely give you an overview of what exactly fusion based approach is and what exactly we can do, and I can give you a head start to prepare and then come up for that session. So yeah, having said that, fusion based approach is basically to fuse multiple sensors to get more accurate, because the more the sensors, the more the data, the more accurate the results are. Correct. So that is the reason we go behind the fusion based approach. I hope the intuition is clear behind going for the fusion based thing. Clear, guys?
Yeah, yeah.
Yeah. So having said that, so these are the things why we go for the fusion be these are more reliable, gives good results for low speed environment, relies more on multiple sensors than one sensor, because more the sensors more good at the data, and specifically can be used in any textureless environment. Like you can't really use camera in a dark space because you can't really know, you won't be getting the features out of it. so you can't really use there. So there could be some other sensors that can definitely be used, like Lidar or such as IMU, or from the wheel speed you can drive the odometry value and you can use in the use case. So you can't always rely on a one sensor but multiple sensors to get the values out of it, and you fuse them to get a proper accurate sensor measurement and the values. Correct. So having said that, in the fusion based approach, there are some certain terminologies that we definitely use around. One of those terminologies, state matrix, observation matrix, Jacobian model. Like I have specifically mentioned here three of the terminologies, but there are a lot of other terminologies known as step noise, state noise, and H matrix, and a lot of things. So, but the underlying three matrices that are predominantly used as state matrix. So, what exactly a state space model or state matrix is basically it's a mathematical equation that represents my motion of the motion of a robotic system from one time step to the next time step. It's basically when my robot moves from current position to the next position, it kinds of determine it creates a model around it, may it be constant velocity model, may it be constant space model or constant position model, and it produces an equation that is like a transition between t to t plus one state. So that is how the state matrix is defined. And as this is a state matrix, similar goes for the observation matrix. So an observation model is basically it that represent a vector of predicted sensor measurement at particular t plus one timestamp. So as the state matrix is for the motion of my robotic system, the observation matrix is used for the sensor measurement. So the values that are given from the sensor are produced in a matrix for the t to t plus 1, added up some noise because all the sensors are comes with a noisy value. So that is how the observation matrix is. And Jacobian model. So this Jacobian model is one of the term that you will definitely hear in all the non-linear systems. So filter based approach are kind of two, like we basically use there are two kind of terminologies. One is Kalman filter, one is extended Kalman filter. So and pretty much in your lifetime you will definitely hear about these two terms, and the basic difference of these two terms is one of the term is used in like linear systems, and one of the term the extended Kalman filter is used on non-linear models. So uh, so to linearize, so when we say non-linear system, we need to our models or our filters can't really work on the non-linear system because it's a mixture of the cosines and sine value and a lot of other stuff. So to linearize the value, we do the Jacobian model. So basically Jacobian model is kind of the partial derivative of the state matrix with respect to the time domain. So it's like we first derive the state matrix, and then we from that state matrix that we get, we do a partial derivative of the state matrix with respect to t to get the Jacobian model, and that Jacobian model is basically used in the furthermore steps that we are going to be using in the extended Kalman filter. I hope this pretty much terminologies, and there are a lot of other points known as step noise and state noise. These are certain noise parameters. As I said, all the sensors comes with noise values and other things. So these are basically all the noise matrices that we involve in the sensor measurements, so as to obtain a predicted sensor measurement out of it. I hope till now all the terminologies that I have sure said you is clear enough. Do you guys have any questions on that till now?
No, no, pretty much clear with that concept.
Y- Yeah. Okay. So having said that, the extended Kalman all the filters works on underlining three processes. One is predict step, update step, and measurement step. So these three are the underlining processes where the whole extended Kalman filter works on. So what does in predict step happens is like it kind of determine the thing that I made you explain in the state space model and the measurement model. So in the predict step, basically the state space model and the measurement model is predicted, like how is my robotic systems with respect to the timestamp, and like with respect to t and t+1, how is it moving, and how is it, how the equations are with respect to my velocity and my time that it is used for the used for the accounting of it. So that is how we determine the exact position of the system, and that is known as a predict step. Upon that, we use a update step. So what exactly update step does is, when I explained you state space model, and one there is a measurement model. So no, one is observation model. So the observation model is kind of determining like it kinds of make a sensor measurement, which is a predicted sensor measurement. So what it does is it continuously computes your like we have a actual sensor measurement and we have a predicted sensor measurement. So what it kinds of does is my whole update step, it kinds of from the actual sensor measurement, using the velocities that I have, I will get a value out of it, and it determines if my actual sensor measurement and predicted sensor measurement are close to it, and that value is determined using a factor known as Kalman gain. So if the Kalman gain and the Kalman gain value lies between 0 to 1, so if the values are in between like more to 1, then I would say my predicted sensor measurement that I got is not to be relied, and I should rely on my actual sensor measurement. And if my values are close to 0, then my actual measurements are pretty good, and I should like my predicted sensor measurement are pretty good, and I should rely on it. So depending on the Kalman gain, my model would determine what kind of equation or what kind of sensor measurement it should take into account, so that it can produce a new form of odometry value. And that after getting the Kalman gain, it determines which set of sensor measurement it should take, and then it goes to the measurement step, where, as I said, we have right now my sensor measurements. I multiply it with the state space model to create a new state space model, and that state space model is a combination of my position, that is x, y, and yaw. So that is how this whole thing is kept into account, and my extended Kalman filter works around on this, underlining these three pretty much steps. I hope that is clear. Like this is pretty much clear here.
Yeah.
Okay, so yeah, so this is okay, so this is a graph where it shows what exactly why do we require the fusion based approach. So here in this graph you can see the yellow line, the blue dotted line is the actual odometry value, and the blue line, the orange line is the visual odometry. You can see there's a huge drift there, but when we fuse the visual with the IMU, so it creates a yellow line which is almost accurate to the ground truth. So from here we can definitely say, like from one sensor we lose out some of the values, but when we fuse two or multiple sensor, it kinds of creates, or it kinds of manipulates, or it kinds of gives certain some value that is not present in the other sensor, and helps in the other way around to get a more good data or more good output as a result. So that this is the reason why we use extended Kalman filter, or we use fusion based approach to get the odometry out of it. And we are pretty much on time, and I had a Python notebook for sure, but the time is already up. So the rest of the things, one of my colleague, as I said, the one of my colleague will make you explain on October 4th, October 3rd. They have a session on specifically on the localization for fusion. So for rest of the understandings, you can definitely join that session, and it will be a fruitful session for you. So yeah, so that's it from our side, and I hope the session is like fruitful and a beneficial session for you guys. And if you guys have any questions, then you can definitely ask us up, and you can definitely reach us out in our LinkedIn profiles. I guess the moderators would have definitely given you up by this time. So yeah.
Hi, Gunjan and Sanket. Thank you for the session. It was a very fruitful one. And yeah, thank you for the session.
Yeah,
Yeah, thank you.
thank you. I guess the moderator is there in the call, or
Yeah, I will now be ready to answer your queries if you have any questions. Anyone?
yeah.
So
I guess there's still time. I guess 8 minutes. So if you just can go back to the slide number 8 of your presentation, the first presentation, if it's okay.
Yeah, sure. Slide number 8. Just a second.
There was
Is my
something
screen visible to you guys?
not yet.
Yeah.
Yeah, so you were saying that there is the position of the lidar and then there is
Hmm.
the ground truth. So
Hmm.
as shown in the picture, from left to right transition, like what is this transition about and how does the position of lidar is different from the ground truth? Like I
Okay.
guess so
Okay.
this ground truth position will be from IMU and like can you just explain about this?
Yeah. Sure. So this basically the picture that you are seeing, it's like a combination of a lot of other things, and it's basically a mapping concept all here. So you can see there's written an illustration of loop closure. So loop closure is basically a terminology that is used in mapping. So as said, all odometry, or like all the, if we are going to determine the values from a single sensor, then we definitely are lacking something or the other, like somewhere the loop won't be closed, or there could be a elongation in the kind of odometer that is formed. So this is a perfect example. So this is kind of, it creates a map around with the help of the lidar, and there's a concept known as loop closure. So my robot tries to searches for the points that is basically that it has seen at some point of time, and when it kind of finds that points, and when it sees ki, yeah, it is here, it tries to match both the points, and when it tries to match the point, it kinds of closes a loop. So it's like it knows this point, and if it is crossing that point, and with some latency or some distance value, so it tries to match those value and get it close. So that is where the loop closure concept comes into account. But yeah, if you see, both the things are ladder odometry only, but here it is like the raw ladder odometry that I showed you, and here it is a concept of loop closure that is taking into account, and then the ladder odometry happening here.
Okay.
Yeah, I hope the thing is bit clear right now.
Like loop closure is basically taking the feedback from
So loop closure is basically kind of getting, so in mapping also there are multiple things. So as if I have to explain on the visual map side, so basically, as my colleague showed you, visual odometry, post visual odometry, it takes up the values from, like, it takes up the odometry values, it kinds of then uses a feedback mechanism to create a loop closure. Post loop closure, it uses a optimization technique, might be some G2O or some kind of post graph optimization, or a lot of other things are there, and then it creates a map around it. So that is how the whole mapping pipeline is all about. But on today's session, we were more predominantly on the localization side, but all the terms that I used right now, like loop closure and the post graph optimization things, tomorrow tomorrow one of our teammate is going to explain all the terms. So yeah, you should definitely attend that, and you will be definitely able to clear all those concepts there.
Okay. Thank you so much.
Yeah, I hope the things are already, like, you guys are pretty much clear, and uh, it's it will be helpful for you.
So I would like to thank you for taking the time to deliver the informative presentation, Sanket and Gunjan. Thank you so much. I would like to thank all the participants for joining us this evening. Thank you, guys.
Yeah, really means a lot. Thank you, guys.
Thank you.
Thank you.
Thank you, Dikshita.
Thank you.
Yeah,
Thank you.
bye bye.